Hello friends and welcome to this video. We are having the second topic from the chapter number 6 titled as adaptive filters, and here the topic is FIR adaptive filters. Adaptive filtering, I hope you people are clear with. It is a focus on non-stationarity here. Now while talking about the filters for signal processing purpose, the very basic two types we are very well known, FIR and IIR. FIR standing for the finite impulse response and the second one IIR standing for the infinite impulse response. So in order to start with the study of the adaptive filters, we first of all take the first, that it is FIR. So the study of adaptive filters by looking at the design of FIR, which is also known as non-recursive type of the filter. So here FIR adaptive filter will be the non-recursive adaptive filter. Now as we compare this one with the another type, that it will be infinite impulse response IIR here. So in contrast to that particular filter, which can be called as IIR adaptive filter or the recursive adaptive filter, this current topic, that is FIR adaptive filter, will be of the routine type used into the adaptive filtering applications that range from the adaptive equalizers that has been used in digital communication systems mostly to adaptive noise control systems here. Now there are various reasons why the FIR type of the adaptive filters are popular here. So we shall be listing three of them, the most important here. So the first one is stability is easily controlled by making ensurety that the filter coefficients are bounded here. So this is the very important point to bring the FIR adaptive filters at the popularity level here. The second point is that these particular FIR adaptive filters, that means non-recursive type of the adaptive filters, are simple and efficient algorithms for adjusting the filter coefficients here. And at the last, the performance of these particular algorithms is very well understood in terms of their convergence and finally the stability. So this is the reason why the adaptive filters of type FIR are very popular, and they are oftenly used while performing enough to satisfy the design criteria, that is for the suitable application. The design of the FIR adaptive filter also requires the estimation of the desired signal that can be denoted by D of n from the related signal x of n here. So this can be better illustrated with the help of the diagram. So in this diagram here you see x of n, the signal, desired signal D of n, the estimate of desired signal D cap of n, and finally the required thing E of n. And here W suffix n of 0, W suffix n of 1, W suffix n of 2, this way up to W suffix n of p are the weights or the coefficients you can see. So mathematically this illustration can be represented with the help of the expression. Here we have D cap of n is equal to the summation k is equal to 0 to p or multiplication of W suffix n of k to x of n minus k, which can further also be represented as W suffix n transpose multiplication to x of n. Here the x of n should be into the small casing, it is a typo mistake. Now here the assumption is that the x of n and D of n are of the non-stationary type. These are basically the random processes. The same aim we have discussed into the previous topic as. So for the current case, here the aim will be to find the coefficient vector W suffix n at the time n, and that will minimize the mean square error here. So here the minimization of the mean square error can be denoted by the Greek letter, I think, psi of n, that is equal to expected value of capital E of mod square of E of n, where the E of n is equal to D of n minus D cap of n, the estimate here, further which can be denoted by w suffix n to the power capital T into x of n here. So x of n should be into the small casing, the expression for the x of n we have represented in the previous video. Now as we have discussed the topic of FIR winner type of filter designing in the previous chapter as well here. So in the derivation of the finite impulse response winner filter, the solution to the minimization problem that we express with the help of the above expression here can be found by setting the derivatives of this representation with respect to the conjugate of w suffix n of k equal to 0 for the values of k is equal to 0, 1, 2 and so on up to small p here. So therefore the resultant representation can be of the form capital E of, we have E of n multiplied to the conjugate of x of n minus k. The value is equal to 0 as discussed for k is equal to 0, 1, 2 and so on up to small p here. So if we have the substitution of this particular representation in the earlier expression, the earlier expression will gets to the form capital E of, inside the curly brackets we have a square bracket first of all multiplied to the conjugate of x of n minus k, where the square bracket involves d of n minus the summation of L is equal to 0 to P or product of W suffix n of L into x of n minus L here. So this value will be equal to 0 for k is equal to 0, 1, 2, 3 and so on up to small p here. So with a little bit of rearrangement of the terms here, we get the new form of the expression where we take the summation representation first of all. So the summation L is equal to 0 to small p or W suffix n of L into the estimate of x of n minus L into the conjugate of x of n minus k. So this is equal to capital E of d of n into the conjugate of x of n minus k, where again k is equal to 0, 1, 2 and so on up to small p. So this is the expression that you can outline, which is basically a set of p plus 1 linear equations having p plus 1 unknowns denoted by w suffix n of L. Now unlike the case of the finite impulse response winner filter, where the assumption is that x of n and d of n are jointly wide sense stationary random processes, the solution to these equation sets will depend on small n here, and here we express the equations into the vector form represented as capital R suffix x of n multiplied by w suffix n. This is equal to small r suffix dx of n here. So here the vector representation capital R suffix x of n is Hermitian matrix of the autocorrelations having the order p plus 1 by p plus 1 here. This is expressed into the matrix form. So Rx of n is equal to the matrix. Here the first row is capital E of x of n into x of n conjugate. The second element in the same row is E of x of n minus 1 into x of n conjugate. In this way, at the last element in the same row we have E of x of n minus p into the conjugate of x of n, whereas the second row is expressed as capital E of x of n into x of n minus 1 conjugate. The second element it will be capital E of x of n minus 1 into conjugate of the same x of n minus 1, whereas the last element of the second row it will be E of x of n minus p into the conjugate of x of n minus 1. So this way the last row it will be capital E of x of n into the conjugate of x of n minus p. The second element E of x of n minus 1 into the conjugate of x of n minus p, and at the last we have E of x of n minus p into the conjugate of x of n minus p here. And the representation on the right hand side of the earlier expression, that it was small r suffix dx of n will be a transpose of the vector representation in this set, where we have capital E of d of n into conjugate of x of n, second element E of d of n into conjugate of x of n minus 1, and this way E of d of n into the conjugate of x of n minus p. So this is the representation of the cross correlations between the desired signal d of n and the input related signal x of n. So for the FIR adaptive type of the filter, we have the vector form representation into the earlier expression, where the LHS and RHS we have expressed with the help of two more expressions here. So if the case will be of jointly wide sense tertiary random processes, the vector form representation will reduce to the Wiener-Hopf equations, and the solution W suffix n of the coefficient will be independent of the time. So for the concerned equation, determination for each and every value of n will not be a practical thing in most of the real-time implementations here. So therefore we extend the FIR adaptive type of the filter design in the next lecture of the same chapter here, where we will be having consideration of the iterative approach based on to the method of steepest descent here. The topic it will be the steepest descent adaptive filter. Thank you.